Hello everyone, I'm Jong-Sung Lee from Seoul National University. Today, I will be presenting our work titled WALT, Leveraging JONAPEN to Tighten the Tail Latency of LSM-Tree on GNS-SSD. This work is done with my colleague Dongwoo Kim and my advisor Jae Lee. A log-structured merge tree is a widely used structure for the modern key-value stores such as RocksDB, LevelDB, Cassandra, HBase, and Bigtable. It can easily handle a large-scale database, which does not fit into the memory space. LSM-tree is designed for a write-heavy workload. Through the conversion of random write pattern into sequential one, the LSM-tree maximizes the storage performance. Joint namespace SSD is a recently emerged storage technique. JNS SSD limits the write pattern as sequential, so it is well suited to the LSM-tree. By exposing the sequential-only feature, JNS SSD provides predictable high performance from the removed internal overhead such as garbage collection. The example shows how conventional SSD and JNS SSD are different. When the host application tries to write data, application locates the data based on the logical block address. Conventional SSD provides the availability of random write by an auto-place update mechanism. Therefore, SSD should maintain the mapping table because the data can be written anywhere inside the device. However, garbage collection should be performed inside the device when there is no empty space, which negatively affects the performance. Let's see the joint namespace SSD case. A host application should sequentially write within the zone and manually send a reset to a zone to reuse it. With the zoned interface, logical block address is directly translated to the physical block address, which contains the zone number and offset. Therefore, mapping can be removed so SSD does not need to run the garbage collection in the background. With this approach, GNS SSD maintains high and stable performance. Because the GNS SSD shows predictable performance, it can be a breakthrough to mitigate the latency spike of the LSM tree. Latency spike is an important problem because it hinders providing the quality of service and system-level agreement to client. We evaluate the GNFS on open-source GNS plugin for RocksDB and plotted the 99th latency in each 1-second time slot. Here is the result. As a result of analysis, the 99th latency heavily fluctuates and reaches almost 70 milliseconds, with 3.5 times longer than the minimum of 99th percentile latency. Despite utilizing the predictable performance GNS SSD, latency spike still occurs. We focus on the batch group write process of RocksDB. It merges the record and write them at once to improve the storage bandwidth. However, this scheme sacrifices the tail latency to achieve the performance. Here is an example. When two pull queries are concurrently issued, they first elect the leader by a synchronization mechanism. After thread 1 is elected as a leader, it generates a batch group and then merges all the key value record of the participants. After merging is done, the leader thread writes the batch group at once to the var area. During the process, thread 2 is waiting for the notification of storage write completion. Batch group write has a negative impact of the tail latency in 2 points. First, synchronization overhead exists while electing a leader thread. Second, storage write overhead occurs because all the threads wait for the write of the whole batch to complete. We proposed a watch which improved the tail latency of the LSM tree on GNS SSD. Our key idea is offloading the synchronization process to the GNS SSD and bypasses the batch group write process of the LSM tree to optimize the tail latency. Also, for further optimizing the tail latency, we introduced several optimization techniques: zone reservation, lazy metadata management, and dummy append. Our evaluation result shows that Watch achieves up to 4.73 times reduction in tail latency while slightly improving the QPS. Now I'll explain the background of our work. Let's see the put query handling in LSM-tree. The query is first stored in the write-ahead log to provide the consistency of the database, and then it is written to the mem table. Even if the system power is suddenly down, key value data can be recovered by replaying the record in the var area. Because the storage is slower than the memory, the time taken by the var write is the highest fraction of the put query handling. According to our evaluation result, updating memtable takes only 2% of the total write latency, and the remaining time is consumed at the var write phase. We analyze the write latency in detail. We break down the write latency into 5 phases: leader election, merge batch group, SSD write, memtable insert, and miscellaneous. The graph shows the average time taken for each phase while varying the number of threads from 2 to 8. We find that even if the number of threads is only 2, synchronization overhead of each leader election takes 38% of writing time, and it reaches 46% in 8-thread case. Only 36% of the time is consumed to make the key value record persist. The join append command is newly introduced, in which the device decides the written location of data and returns the address via the assigned LBA. By offloading the responsibility of configuring the LBA from the host to the device side, the append command can concurrently execute even if the sequential write constraint exists. We will use the join append command to skip the batch current write. Let's see the example flow of write and append below. In the case of the join write, the application should specify the target LBA for each write request. We assume that the target LBA of each thread is LBA2 for thread 0, LBA4 for thread 1, and LBA3 for thread 2. If these write requests are transferred to the device concurrently, execution order cannot be maintained inside the device. We also assume that the device handles 3 commands in the sequence of thread 0, 1, and 2. The target LBA of the write request of thread 0 matches the write pointer. Therefore, write succeeds, and the completion is returned to the thread 0. However, when the device tried to handle the write request of thread 1, a write pointer mismatch happened. The requested LBA is 4, but the write pointer inside the device is 3. Therefore, the write request of the thread 1 is aborted. Thread 2 requested the write at LBA 3, which is currently matched to the write pointer. Write succeeds, and the completion is returned to the thread 2. Because of the sequential write constraint, it is impossible to write data concurrently. Let's see the append case on the right side. The append command does not specify the target LBA from the host side. It just specifies the target join and the data to be written. When the host delivers the append command concurrently, the device can freely decide its handling sequence. Let's assume that the device fetches the command in the sequence of the thread 0, 2, and 1. GNS-SSD is now responsible for configuring the LBA. The current write pointer is 2, so it stores the data of thread 0 at LBA2. It updates the assigned LBA field of completion entry to notify thread 0 that the data is written to the LBA2. Then the append command of thread 2 is fetched and stored at the LBA3. Like the thread 0, LBA3 is notified by the ALB field of completion entry of the thread 2. Finally, the append command of thread 1 is fetched and stored at the LBA4. GNS-SSD records the ALBA field as 4 for thread 1. By offloading the responsibility of determining target LBA to the device side, append command can be executed concurrently. Now I will introduce our technique named Waltz. This is the overall structure of Waltz. There are 2 main components, join manager and replace checker. The join manager is a background process that manages the join for the WAR file. When the join replacement case occurs, the join manager allocates the join for the WAR file. Also, the join manager handles the evicted joins from the WAR file to be finished and closed using the management commands. Replace checker is triggered right after the completion of each join append to the WAR file. It checks whether the remaining space of the WAR file is enough or not. If the remaining space is smaller than the threshold, the replacement process is triggered. Under the replacement process, a leader thread is elected by a lock-free mechanism, and then the leader allocates a new join by retrieving the allocation queue of the join manager. Finally, it switches the new join with the active join of the WAR file and updates the extent list and join status. I'll explain the write path example in detail. When the book call is delivered, each worker thread generates a WAR record. The WAR record bypasses the batch current write process and directly written to the WAR file. After finding the active join of the WAR file, Waltz generates append command for each record and issued it to the active join. When the completion occurs, the replacement checker of Watch retrieve the assigned ABA of the completion entry. In the thread 1 case, the record does not exceed the configured limit, so it just returns and goes through the memtable update phase. Also for thread 2, the completion entry is retrieved by the replace checker, and watch detect the exception occurs. To allocate the new zone for the var file, watch elect the leader thread, and then allocate a new zone from the zone manager. In this case, we assume that thread 2 is elected as a leader. The allocated zone is registered to the var file by switching the active zone. While the leader thread is switching the active zone, other threads can append their record concurrently. Therefore, retrieving the exact right pointer of the replaced zone after switching the active zone is necessary. Based on the right pointer, the leader thread calculates the extent information and record it at the extent list of the var file. After all the replacement process is done, the leader thread returns to update the memtable. Watch also introduced several optimizations. Because the zone allocation for the var file is triggered in the replacement process, allocation latency is also included in the write latency of replacement leader thread. To minimize the tail latency of exception case, we reserve two zones and maintain them inside the allocation queue so that the allocation does not hurt the write latency. When the var append happens, the status of the zone, such as the write pointer and remaining space, should be updated. Under the var system, we update the zone status only when the zone is evicted rather than update the status in every var append. Therefore, watch can minimize the time consumption of metadata update in the put query handling. In the replacement case, the leader thread should retrieve the right pointer of the evicted zone. Under the NVMe GNS protocol, there is a management command named zone report, which requests the zone's metadata, including the right pointer. However, it takes too long time, which is measured to almost 7 milliseconds in our test. Instead, we use the zone append command for a single sector, which only consumes 93 microseconds on average. We calculate the right pointer based on the received assigned ABA. Now, I will explain the evaluation setup and result of Vouch. To evaluate the Vouch, we use the Samsung NVMe GNS SSD, whose zone size is 96 MB and the total capacity of the device is 4 TB as our target GNS device. For the baseline system, we use the SPDK integrated GenFS as a baseline. We use microbenchmark, which tests the get and put queries while varying the write-read ratio and the key distribution. Also for real-world workload, we use the mixed graph benchmark, which is the synthetic workload that mimics the social graph workload with query composition and key access pattern. In all the evaluation, a 256 GB database is generated by sequentially filling the key and values, and then 20 million queries are evaluated with 4 KB size key value pairs by 4 worker threads. Under our evaluation, Watch shows up to 4.73 times reduction in tail latency by removing the synchronization overhead of batch quorum write and introducing several optimizations. In the case of QPS, Watch shows up to 11.7% improvement due to the write pace optimization. We also measure the 99th percentile latency over time. We record all the write latency of put queries, gather them within the 1 second time slot, sort, and pick the 99th percentile latency. As the graph shows, the baseline system fluctuates from starting point, and the degree of fluctuation increases over time. This is because the test starts from the clean state, which means that the background operations such as flush and compaction rarely occurs at the starting point. Watch also shows the similar aspect. The 99th percentile latency also fluctuates in Watch, and it gradually increases over time. However, Watch shows flat and stable result at the beginning of the test, and the degree of the fluctuation is much lower compared to the baseline system. This also shows that the Watch system effectively improved the tail latency by leveraging zone append to remove the batch quorum write. As a conclusion, we propose Watch, which leverages the zone append command to tighten the tail latency of the LSM tree on GNS SSD. Watch introduced several techniques for latency optimization, zone reservation, lazy metadata management, and dummy append. By removing the synchronization overhead of batch-cron write, Watts achieved 4.73 times reduction in tail latency. Thank you for listening.